So, all right, so we continue with the second session. So just a quick note, for the next week, the live sessions may be on Friday, just for the second week. I will inform you before next Tuesday. So just for next week, it may be on Friday. But anyway, like if you're able to attend the live session, you're able to watch later. So what are we gonna do? So we have actually completed the introduction. Like I want to just show you a quick example of quadrature. Okay, so why we need it first as the introduction. So so I said like we are going to restructure the governing equations in FEM. For example, we're going to have this kind of equations. Well, let's say d square u over dx square plus u is equal to some function of fx. Okay, so in FEM, what we're going to do, we're going to multiply this with a test function v. So I'll teach the theory later, but with a test function v, but it's like or rate function, something like this, and then integrate over the domain of interest. Okay. For example, I'm going to have like the equation is going to be multiplied with the test function v, for example, dx integral over omega. Okay, like dx integral plus integral u v dx, okay, is equal to f v dx omega. So this is like what like we're going to deal with equations like integral equations. So that is actually going to require us computing some integrals. For example, this one. So the integrations in this class will be treated numerically. So we're going to write down some simple routines to be able to find, like integrate y. For example, let's start with a simple example. Like I want to integrate, for example, -1 to 1. Let's say x squared dx. Okay, so this is I know it is simple in terms of like integrating this analytically. Let's do it first. Like it's x cubed divided by 3, which is going to be related from -1 to 1. So what is this? Like 1 divided by 3 minus -1 over 3, which is equal to 2/3, correct? So I would expect, okay, this is the exact solution. So, but we in FEM also, like we're going to need this kind of integrals. This is going to be either like one-dimensional or multi-dimensional integral. So I'm going to integrate some functions here, which is going to be a function of space, and it is going to be different for each portion of this, like the domain. And we're not able to find actually this kind of simple analytical integration. So we need actually a numerical integration. And this numerical technique, like one of them, is known as Gaussian quadrature. So I'm going to teach you the theory of this technique later. Actually, finds the exact integration of polynomials. For example, like I can integrate this exactly using a Gaussian quadrature by, so I'm going to just write here theory is later. So today I'm going to show you a little bit like a quick implementation. That's why I'm going to show you, for example, any integral of f of x dx from -1 to 1 can be actually found by a summation of the like multiplication of the weights I times the f evaluated at some integration points fi for I is equal to 1, 2, like I call it like NGP to stand for number of Gauss points. Okay. So it's kind of like what I see. Instead of doing an integral of this from -1 to 1, f of x takes analytically, I'm able to write down a function which actually finds the exact solution, of course, with the use of required number of Gauss points of the type of f of x is the polynomial. Like if I have a polynomial of f of x, like then I'm able to integrate it exactly. And also like it gives very accurate results, even if the f of x is not polynomial. But in FEM, as long as the f right-hand side, like any external force is not in the form of like a complex function, the approximation or interpolation of the governing equations is going to be done by the polynomial. So the resulting equation is going to be like whatever here is the integrand is going to be polynomial usually. Some integrand. Yeah. I mean, this is going to be like, I'm going to show you like where does this come from later. But this is, let me just maybe change the color to show you, like this is going to be the Gauss weight. And this, again, the argument of f is going to be the Gauss point to be evaluated. I mean, I'm going to evaluate the function at that point, Gauss point. Okay. So I is going to from 1 to NGP, and depending on like the how many number of Gauss points we use, actually it's going to I mean, you don't have to use more than enough if this is polynomial, but if it is not polynomial, for example, if it is maybe like trigonometric function, then I need to increase the number of Gauss points to increase the accuracy of the numerical integration. So, but how am I going to do this? Like for any f of x, I need to write down a function now. How are we going to do this by coding? The first thing is I need to actually find this stuff. What is this? Like, how am I going to, where do I get this? Like, I'm going to show you like for how we're going to find the weights and Gauss points, but this is already tabulated. So we just go to Google. Let me just have it. Yes, I have the Google. Like what you Google is Gauss points and weights. Okay. For example, this one, the first link, just Formax GitHub, actually has all tabulated. Like this is kind of like what I have written, like the theory of the Gaussian quadrature. And like here, what we see is like the weights, and the abscissa here is actually the Gauss weight. Okay, so now what I'm going to do, I'm going to show you how we're going to implement this kind of integration to the MATLAB. Okay, I need to record the weights and I need to record the Gauss points. Like this is for number of Gauss points too. Like n here like refers to the NGP for like the one I have written. Like NGP is like n. Okay, so this is same as n in Formax. Okay, if you want to like just type. So what I suggest you just do the same thing if you have access to MATLAB now or later, and if you have a question, ask during the session. So what I'm going to do now, I'm going to actually first, like I want to save actually the values of the Gauss weights and Gauss points. Of course, I'm going to keep them in an array. So now I'm going to bring the MATLAB if I have, actually not this one. Okay, so this is, okay, it is in your folder. So in MATLAB, like I'm not teaching how you to use MATLAB, but this, or just not about like using the MATLAB anyway, you're just using the simple interface, like the script interface. So I have just pressed the new script button. So this just brings you a simple interface, kind of like a file you're able to write down anything you like in terms of coding. So this is actually C based, but what we want to do, like I want to write down or first like to define the Gauss points and Gauss weights. So if you want to write down like as a comment, we use the percentage sign. So it is like Shift 5 in my case, but you can just use this button. Let me just make this a bit bigger. So I'm going to write down just a very simple comment. So like the Gauss quadrature. So, and I want to first keep the Gauss points and weights of order 2. First, let's make it order 2, okay? So I just come back to the POMX and just take all this one and just copy, okay? I need to restructure, I guess. Okay, anyway, so I have like, just copy it. So I need to just keep all of this in arrays, okay? So let's say this is the Gauss weight. 1 is equal to 1. Semicolon is used not to print to screen. So just use semicolon after defining anything. Or the Gauss weight 2, it is going to be again 1. So it is like the same weights actually for this case. Command X. So then I need to define Gauss points. Gauss points GP1 is equal to semicolon. And I need to, I'm just doing for you, I assume you know nothing about coding. So this is like definition of the elements of 2 different arrays. These are one-dimensional arrays. Gauss weights and Gauss points are the names of the arrays with 2 elements. I mean, the reason like I use the MATLAB interface for undergraduate students, because you don't have to deal with the like definitions of arrays. If you use like CPP or Python, blah, blah, you need to first define the array, their length, blah, blah. You have to specify the size, but you don't have to do it here. Like in MATLAB, you don't have to worry about that. Like it just understand, okay, this is going to be a size to array with even you don't have to define the types of the elements. Now this is going to be like we don't have use like this is going to be double, of course, because I have defined like 1.0 something is not integer. The number of the arguments for the arrays are going to be, of course, integer, like the first element, second element. So what I did, I just keep the weights and the Gauss points in corresponding arrays. So what I want to do, okay, so I'm trying to integrate. So this is actually the first example. That's why this is for domain between -1 and 1. So I'll move to the other problems later, but this is just integral for -1 to 1. So what we want to integrate. So let's go back to this note. It says I'm going to sum the function evaluated at the Gauss point multiplied with the weight from 1 to NGP. Now, so what is the NGP here? NGP is actually 2, but I can read it from the length of Gauss weight. Like it is going to be 2. Let me show you, like if you, this is the editor for the script, but you can always use the command window. For example, if I just define, let me just, like you can always come here and then right click evaluate the selection in the command window. And I just evaluated, I already defined the 2 arrays, which is shown on the workspace. So if I want to just, for example, see what is the length of this GP array, for example, it is 2. If I want to see the W, like it's the length of the array is going to be 2. The number of rows, actually, not rows, columns for now. So I have like 2 arrays already defined. Answer is just the one like already MATLAB defines because I'm asking for something. So this is just a random thing. So if we want to clear anything in the workspace, just type clear. Everything is gone from the workspace. If you want to clear the common window, CLC, enter. Okay, so, and I suggest usually like writing on the top of this your little routine like CLC to clear the common window, also like to clear all the variables, because they maybe you predefined it and they have different size, you may have problems later. So clear everything and just define. So it says the integration is actually is going to be computed by numerically by using the Gaussian quadrature. It says, okay, I'm going to multiply the weights with the functions evaluated at the Gauss points. So then I need to sum like these multiplications from 1 to number of Gauss points. This means I'm going to have a loop. So for loop, for example, if I define for I is equal to 1, 2, and GP, like number of Gauss points, and add the for loop. So inside this for loop, I'm going to sum something. Let's say the I, let's just define I now. I is equal to 0. Like this is going to be like the summation. We're going to sum over I. I is equal to I plus. Okay. And then it says, just go over I, take the Gauss weight at the node I, multiply it with the function. I don't know what is the function. Let's say this is F. And I'm going to evaluate this at the F. Okay, so what is F? So actually it was X squared, but we never write X squared. Okay, so because this domain is now specific, which is the between -1 and 1, we don't have to actually map the X to the integration domain. Like it says, like if you come back to the summation, it says, okay, find the value of F evaluated at the Gauss point. So what I'm going to do, wherever I see X here, actually, I'm going to write down, which is going to be evaluated at the Gauss point. It's Gauss point I square, and semicolon at the point onto the screen. And this is the end, I guess. So if you want to see the result at the end, just write I. It's going to print it to the screen. Let me just bring it to the help and show you the result. So if I just run this, let me just save first to the lecture. So G1, whatever it is. So the code name is just very simple. I mean, this is kindergarten level. Okay, even like kindergarten level children can write this kind of coding. Okay, so if you're not able to do this yet, so no worries. Okay, you still have time. So just run this by, there is going to be, let me just a bit extend this, like through, I mean, this is the beauty of MATLAB for undergraduate teaching. You don't have to compile the code. Run is going to run something. It says 0.6667. So what is this? Is it 2/3? Okay, so I found row already. So whatever the function is, I need to only change this. This is actually X squared, okay? So what if I want to find the X cube? You don't have to do anything. Just make this 3, okay? And you will just rerun it, okay? So it says it is 0. Why it is 0, X cube, the integral of X cube from -1 to 1? Huh? Any idea? From here? Why do you think the integral of X cube is? Because it is odd function? Because like the -1 to 0 and 0 to +1 are going to cancel each other. Okay, so it's something like this. Like if I, like this is the X square. I mean, it's not the correct one, but something like this. I couldn't plot it, was like something like this, but the X cube is something like this one. So this portion is going to cancel this portion. So it's going to be end up with the 0. But this is of course non-zero. Okay. So this is your code number -15, level -15. So it's kind of like giving us the integral of very simple polynomials. Okay. But this is order number 2. Okay. What if I want to increase the number of, I mean, the order of the integration? Because the increasing the number of Gauss points and the weights is going to increase the accuracy of the integration if the function is not simply polynomial. Okay, we may have this kind of situations, and for example, let me just show you something from Google again. Where is my Google? Okay. So this is just one thing. Let me just here take Google. There's actually Wolfram Alpha if you like to check some integral results. For example, if I want to integrate something, they have also like a same routine on the background working, like just read it, like the one we have written already. Something like this is working on the background of Wolfram Alpha, like, but this is kind of like the online version of mathematical. For example, I want to integrate x square from negative 1 to 1. So let's see the results. So it should be like the same, 2/3. You see it, like it's like there's going to be like analytical result as well as blah blah. So this is how we actually define the solution. This approximate solution is actually found by applying this kind of technique. Okay. So what if I want to integrate something like, maybe I multiply with the sign pi x. So what's gonna happen? It's actually made it odd. So let's make it cosine. I want to see something non-zero. Okay, so what I see is like the result is actually the function is a bit complex in -1 and 1, not that simple. Like the and the result is like -4 over pi square, something -0.4. So I'm going to compute this now. So if I just compute this result with the order 2 Gauss point, let's see what we're going to obtain. So we said it is going to be cosine pi x. What is x? Evaluated at the Gauss point I. So this is the same as, the comment is now x square times cosine pi x. So we never write the function explicitly. Okay, so we just evaluate the function at the corresponding Gauss point. So let's just run this. So it says I have negative 0.16, quite different than this result. You see it? So the reason is because the order number 2 for integration is not enough. This is exact for certain polynomials, but it's not actually enough. So what are we going to do? Why don't we increase the number of Gauss points and Gauss weights? So I just go back to quadrature. Usually 7 is enough. Okay, so I'm going to copy all. What is it? So I'm going to rework on the array. So I'm going to make this now 7 and restructure everything. Now this is going to be Gauss weight 1. This is like I'm going to just copy and paste everything here and modify to be able to define actually for you. This is going to be 2, 3, 4, 5, 6, and 7. If you work with CPP, you need to start from 0, the index number. So this is going to be Gauss point 1. Copy everywhere. 2, 3, 4, 5, 6, 7. And I also need to put semicolons. I don't want to print everything to the screen. If you don't do this, it's going to print to the screen like this one, for example. I didn't put a semicolon here, so it just prints the value of I onto the common window. Again, boop, 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 boop. Okay, and then equal. So I don't change anything, just change the values of the Gauss points, and that's it. So that is the 7. Like you can comment this if you like. There is a comment section here, or everything's comment, run. So what I get now, 0.4053. So this should be actually almost close, almost the same actually. So we got the same result. So usually like 7 is going to be enough for some, I mean, if it is too complex, like LLF oscillation, blah, blah, I mean, within the domain for the function, of course, you need to increase the number of resolution, but usually this kind of like functions like this one, at least, when we are able to compute almost correctly the integration. So what is this? So I didn't use any command or library from this MATLAB or Mathematica. I just have written this as a very simple script. I can do this in any language, doesn't matter. But it works, at least now for -1 to 1 for the kindergarten level. So any question? Okay. No question? Everything is clear? Come on. Okay, do you want me to pick one? So how many minutes? So we have spent almost 15 minutes, I guess. How many? 25? Oh no, 25 minutes. Yes. Yes, that is the later. I'm going to teach the theory later. Because the Gauss quadrature is able to integrate exactly the polynomials of order 2n minus 1. Like if the polynomial of order n, I want to integrate it exactly, then I need to use 2n minus 1 is equal to, like, put the like there's going to be like a theory behind this. I'm going to teach it later. But if you have any question in terms of even the script here, please do ask now. Very big, like, just maybe this is maybe your first time you're writing this kind of stuff. I don't know. Question? Because I'm going to convert this to a function now. Hello.
I have a question.
Yes.
Where does the come from Gauss weight and Gauss point values that you write?
Oh, I told you I'm going to teach that later. There's a
okay.
theory behind it. Like we're going to actually find the roots, even like for like the ones here. I'm maybe on the next lecture, I don't know. I'm going to show you where does this come from.
Will we find these numbers, or is there already there for the use?
No, I'm going to show you how to find, for example, the order 2 Gauss weights and Gauss points. And it is the method how you find. But usually, like what we do, we just take this from the order computer tabulated values. We just like say,
just take them, right?
Yeah, that's it. Like the ones I have used already, POMX, for example. You can just take even like the order 64. I don't know, like they have 256, I guess, at most, maybe 64 here. But like I remember in one of my problems, I needed 256. I remember I used that because it was a very complex integration. I remember I had to increase the resolution a lot. But I usually like 7 is going to be enough. So as long as you like keep this, that is going to be okay. Okay.
Okay.
But I'm going to teach you like where does this come from, and how we obtain the Gauss weights, Gauss points, and you understand this theory. Okay, then you should first trust the method because it gives the exact results, correct? Like we saw, like even if it is not a polynomial, like this is not a simple polynomial, trigonometry plus multiplies with another polynomial, it's complex enough. And what I see with 7 Gauss points and Gauss weights, I have computed exactly, I mean, the same as the Mathematica, I guess, which you may like a lot. Okay. So I'm going to show you how are we going to, should we convert this to a function actually? Maybe we never.
Sir, I can ask a question.
Yes, sure.
How can we know true n values when we know exact value of n or integration?
If you're asking for the polynomials, there's a way. But if the function is polynomial, there is a way. Like you don't have to use like more than some defined, I mean, it's going to be exact anyway if you use like the two number of Gauss points or Gauss weights. But for non-polynomial cases, usually you don't know much. You should be able to familiar with the function, like the one you use. You should just see the function plot, for example, in the domain. If it is not that complex, I mean, this is going to be all, usually it is enough, just this is from practical point of view. But if it is polynomial, there's going to be way, like I'm going to teach you on the 6th week, I guess. Like if, where am I? Like I'm going to show you like the start from the 0th order and then integration of 0th order polynomial, and then we go up to like 3rd order polynomial to be able to find the weights and the functions. So what is the actual simple idea is like if we have an order 2n minus 1 polynomial, like let me just write here if you like. So this method integrates polynomials of order 2n minus 1 exactly by, maybe I said something reverse in to ask me something, but I said something 2n minus 1 by using n order quadrature. Okay, so I'm going to show you the theory later, but this is just the first lecture. So what does that mean? For example, I want to integrate x cubed. For example, f of x is equal to x cubed. So this is order 3 polynomial, correct? That means the quadrature, I mean, the numerical quadrature is going to be find the exact integration, not the approximate, exact. If I use two, I mean, the n minus 1, I'm going to equate this to the order of polynomial, then 2n is equal to 4, n is equal to 2. That means if I use 2, like the first one we used, 2 Gauss weights, 2 Gauss points, then I'm going to, like, I'm able to integrate the polynomials of order up to 3 exactly. So there's no need to use 7, for example, for this example. It doesn't have to be x cubed, like it can be something like this, ax cubed plus bx squared plus cx plus d, doesn't matter. So this may be any function, like b may be 0, c may be 0, a may be 0, doesn't matter. Like up to this order, the Gauss quadrature exactly integrates the polynomials of up, like if you use n is equal to 2 points and weights. So this is going to be the exact integration. Okay.
Thank you.
I hope I have answered your question. Yes. Okay. So I have 5 more minutes. Maybe I should continue with how, like this is just a script. So could we just write a function? Like maybe there is integrate in MATLAB. I don't know how to do it. Really, I don't know. I should come back to Google. Numerical, let me just write here. Numerical integration in MATLAB. I don't know. Maybe there's a function already. That's like there's like trapeze, blah blah. But I should write the function as this and then integral blah. Okay, it just takes an internal function definition. So let's use this. Okay. Like I just copy it here, function f is equal to exponential. Let's change everything to our problem, cosine pi x. And this was, I guess, x squared. So this was our function. I have defined an inline function, MATLAB f. And it says integrate this, q is equal to this. I don't know. But with this is the boundaries from 0 to something. Our boundaries are negative 1 to 1. This is my function f and q. So I found the same thing. So I don't know what is integral. Maybe just if I don't know how to even open integral. What is it? Integral. Like let's go to that sub function. Oh my god, they have like some actually not, they are going actually referring to other stuff, I guess. Some functions, error messages. There is the integral calculation. It actually goes to this function.
Hocam integrali yanlış yazdınız ondan mı hocam?
No, it's okay. I found it. It corrected now. So integral. I'm trying to write something wrong. That's why. Why it doesn't go to there? Maybe I should write open. I don't know. Not fonts. So what is this? It's actually copy. I don't know the name of the function, so maybe there is. It's integral calc, the function. I don't know. I don't know where is it even, like it's some function background in the MATLAB, whatever it's. We're not able, we don't care much about it. Like it may be like complicated. It may just consider a lot of situations. What if the user inputs some integers, non-numbers, blah blah, a lot of stuff. We're not interested in with that stuff because we're writing the solver. I mean the little scripts that, I mean, the users are us, so we know how to use it, so we don't worry about that kind of like the details. So now the question is, how am I going to write down a function? So I want to show you that as well. But how we can use the function like this one? Like if you see, for example, it actually takes an inline function. Do we need this? Maybe we can convert some, I don't know. Which we can write any function, doesn't matter, but I mean, like for now, what should we do? I'm thinking about it. Maybe like Gauss weights, Gauss points may be called from some other function. Yeah, maybe we should do it now. Okay, I'll start maybe next section. How we can convert this to some other function. Like maybe we can define every order from the function, and it will return us the corresponding Gauss weights and Gauss points. Maybe after the break, okay? So I'm going to just remove that part, write it as a function, and you can increase the number of orders, just save everything inside, copy from the Poemax maybe, and it will, depending on our choice, maybe it is going to, just to show you like how to write a simple function, okay? So if you don't have a question, I have less than a minute. Probably I'm going to stop and give a 15 minutes break and then continue with the function writing, simple function writing in MATLAB. All right, okay. So let's stop sharing and stop recording.